Hello, everyone. Welcome to this week's podcast. This week's podcast is going to focus on recent research insights, specifically related to forest biomass and carbon estimation. For a little bit of background on this, I presented at the California Air Resources Board's U.S. Forest Products Compliance Offset Protocol Workshop, and this was actually just last week. And what I'll talk about today is largely the slides that I presented as a part of that workshop last week. And I'll include a link to the slides if you want to follow along or want to have them for reference in the future. But anyway, I think there's been a lot of insights, a lot of research that's come in the world, really from the forest biometrics community about new ways, new improvements to estimating forest biomass and carbon. And so if we look back at the history of biomass and carbon research, when we look at applying biomass equations to individual trees to estimate how much biomass and ultimately how much carbon is found in those trees. I'll take you kind of on a 20-year history of that in the United States anyway. The Jenkins biomass equations are some of the most widely used equations in the forest biomass and forest carbon world, and those were developed in 2003, and they're still widely used today. There's been a lot of folks that have used those equations, I think because they're relatively simple to implement to a forest inventory. If you have a tree list and a species list of those trees, these biomass equations developed by Jenkins and others in the early 2000s were quite robust. Well, the U.S. Forest Service around 2011 started to develop a new method for quantifying biomass and carbon and volume in their individual trees. And this led to the development of the component ratio method as a way of finding out how much carbon is in our forests. And so for a long while, and that's still used, those equations are still used in many forest inventories that assess biomass and carbon today. Not long after the publishing of those new sets of equations, lots of folks in the forest biometrics community were really interested in improving the methods for estimating tree biomass. And so if you look historically, a lot of the work had been done on using kind of already developed equations. Most of those equations weren't even used or haven't even been updated in decades. And so certainly with changes to the landscape and changes the way our trees are growing, there was a call to improve some of the ways that we estimate biomass and carbon. And that all led to this year some new equations coming out that really focus on new and updated volume, biomass, and carbon equations for several of our U.S. tree species. And this project was led by the U.S. Forest Service along with a number of universities that tried to look historically and gathered hundreds of thousands of records of tree biomass and carbon from studies in the past, and then also sampled and felled a lot of trees to get biomass and carbon measurements for some of the species and some of the ages and sizes that they were kind of lacking. And so what's really important about those new volume and biomass equations is that they show an increase in the above ground biomass across the United States. So across all regions and across many of the species, we're seeing more biomass, more carbon in trees compared to the previously used component ratio method equations. And so what's interesting is if you look at the data, obviously if we look at trees, most of the biomass is in the stem or the bole of that tree. But this new set of equations that have been developed that show an increase in biomass, what they're seeing is that it's actually an increase in the tops and the limbs of those trees. And so it's really interesting to see that, when you think about all the studies that fell trees to determine biomass, you think most of the biomass is in the bole of the tree. But again, this work kind of found that if we incorporate the tops and limbs, there's an incredible amount there as well, which led to a lot of the increases that they're seeing in above ground biomass. So those equations are not necessarily out yet. As my understanding is, they'll be updated to the US's Forest Inventory and Analysis database quite soon. And then I think as word gets out that there are these new equations developed, they'll eventually spread and I think will be included in forest inventories here in the near future. Another interesting research finding is this idea that 50% of the biomass of a tree is carbon. And there's been some work coming out that says that's not necessarily true. 50% might be a pretty reliable assumption, but if we look at live trees and dead trees, if we separate out the live tree components into the stem and roots and branches and the bark, the 50% assumption fluctuates, and there are some uncertainty bounds around it, depending on the species, depending on the status, live or dead, and comparing that to the different components within a tree. And so there's been some work done in compiling a database that's looking at trying to come up with a distribution of carbon fractions. And so what you can see in the graphs that were provided in those studies is that the 50% assumption doesn't necessarily hold for a lot of these different components within a tree. And so I think it's important to understand that although the 50% assumption is a nice, easy one to apply when we're summarizing forest carbon data, it's not always going to be the case that 50% of the biomass is in carbon. I think another big research insight that's come out in recent years is how we quantify forest disturbances. I think there's a lot of information out there now. National forest inventories are collecting quite a bit of information. But the thing I point out is that how we quantify those forest disturbances really matters. And so as an example, in the U.S.'s Forest Inventory and Analysis Program, they quantify disturbances in a number of different ways. And so one could be kind of assessing at the plot or the condition level, what's been going on here? And it can be easily said, well, oh, there's a fire that impacted the plot. And so that might be how that plot is coded so that people that use the data might understand that something went on here. However, there are also a lot of individual tree metrics, such as the agent of mortality, such as the tree damage code, that field crews measure on every single tree. And so I think what you result in is different ways to quantify disturbances depending on what matters to the analyst, to the organization that's looking at the data. And so there's a great figure from a recent grad student that did an analysis of this that you can see in the slides that really shows a map of the U.S. in different colors based on the same disturbances, really pointing out the fact that forest disturbances really matter in terms of how you quantify them ultimately, perhaps for some use in a forest carbon assessment. I think another thing to recognize is that we've been tracking forest disturbances differently through time. And so I'm thinking of one paper that recently came out that focused on the northern lake states. And this one was really focused and really pointing out that most of the disturbances are increasing in our forests, at least in the last 20 or so years since the FIA program has been implementing an annual design where plots are visited annually, or a full cycle of plots are visited annually. One plot is measured about every 5 years, 5 to 7 years in the eastern United States. But an important thing to see there is that we've tracked disturbances differently through the time series. And so back to the year 2000, the inventory collected 16 different numbers of disturbances. You can think of those as things like wind damage to a forest, fire, animal damage, kind of the main disturbance agents like that. But then by 2008, the program was collecting 28 different disturbances as a part of the FIA program. And so that can really matter. So that would be an example of kind of becoming more refined in what kind of disturbance agent might be listed. So instead of just animal damage, a plot might be coded as animal damage with browse from white-tailed deer or something similar to that. So I think it's important to recognize that disturbances are really important to understanding changes in our forests, but we also need to understand the whole time series, particularly if we're looking at a long time, to get a sense of what disturbances have shaped our forests. Another big topic that's recently come out of the forest biometrics literature is small area estimation. And this is generally considered whenever you use a statistical approach that improves the precision of forest inventory estimates for a small geographic area. And so this can include additional data beyond the plot measurements, So it could include data kind of from a nearby spatial location, or it can include a data from a completely different data set, like remote sensing. And the reason this has seen such a large number of interests from different users is because it results in more precise estimates. And so there's an excellent graph in the slides that if you were to look at kind of the traditional way that the Forest Inventory Analysis Program develops its estimates of, say, merchantable volume or biomass or carbon, you can get some pretty large error bounds around those estimates. However, if you incorporate some additional data, whether it be another model, or what we might call a model-based estimator, you can result in tighter bounds of uncertainty around your estimates. And so that's incredibly important as we think about wanting to have a reliable estimate of our forest carbon resource as one example. I point to another case study of this that looked at integrating forest inventory data with remote sensing, and this was a study in New York. And so what they did in New York was they had these different collections of LiDAR across different areas of the state, and they wanted to basically use the forest inventory analysis plot data along with this LiDAR collect and some other topographic and climatic variables to get a sense of what the biomass might be across the state of New York. And so they found that they produced a 30-meter above-ground biomass prediction surface with combining these different data sources, and they were able to explain up to 80% of the variation in the field observations of biomass at the plot level. And so it just goes to show that integrating different sources of data through a small area estimation technique can result in a precise estimate of your unit of variable of interest. I'll finally say that there's a lot of information, a lot of tools out there to access information related to forest biomass and carbon. The FIA has done some revamping to its DataMart page and its eValidator page. DataMart being a great tool that can access FIA data, typically by the state level, and eValidator being a great tool to estimate population level parameters for a state of interest or a specific location of interest. And there's been a lot of great support in the user community in some of the software packages like R, a lot of great packages coming up and being used to access and to deliver FIA data directly to a user. And there's been a lot of outreach and different kinds of tools to help interpret some of the FIA data as it relates to forest carbon. And then finally, forecasting forest carbon is still a big part of a lot of different forest carbon programs, and as you think about markets and things like that. And so one of those tools, especially in one of the programs that CARB has, is the Forest Vegetation Simulator, which serves as an approved growth and yield tool for carbon accounting. And so it's important to understand that this is a great tool to help forecast what carbon might look like in 10 years, 50 years, 100 years. And in a tool like FPS, it's been really improved of recent years because the developers have improved the user interface. It's now available as a web-based browser, so there's no need to download any external software. And they've also made the source code available if you wanted to go and take a look to see what are the equations that's driving this model or this component of the growth and yield system. However, one of the things I stress is that we need to continue to develop and integrate new equations and to validate and benchmark tools like FVS to make sure they're depicting forest growth correctly that we might expect. And so that's going to rely a lot on long-term data from experimental forests. It's going to rely a lot on people continuing to update and validate and benchmark these models as we look to better understand what our forests look like in the future. And so that's it. Those are kind of some topics and some insights that I think are really important to understand as it relates to recent research in the estimation of forest biomass and carbon. Thanks for listening.